Is it the day before the Regents exam, maybe even the day of, and you want to be better at it, but you're not sure how? Have a look at this video. This year I had 59 students take 400 questions, though they didn't all take all of them, from the 2002 to 2013 exam. It's a 966 question pool. Of those, these are the most missed categories of question in order. Now, if you're really curious where those categories came from, I did it in my own program here, which you can download to use on a PC Excel. I'll have a link in the description and on a card at the end. You can magically pick a topic and go through questions from whatever you need. For example, some of the most missed questions are these ones on estimation. Students hate these. But enough about that. Also, these represent all the Regents questions from 2002 up until 2018. This is the distribution of topics. In that time, there have been 1,216 questions. Let's try to unlock some of the secrets. If you don't want to see the answers, avert your eyes, but these are the top 40 most missed questions by my students and what percent they got right or wrong, and these are the topics. We're going to go through these 40 quickly. If you'd like to see the questions yourself, you can look in the description to download a PDF. And if you like this method, I've also done this 3 years in the past. That'll also be linked in the description and on an end card at the end. For each question, I'll let the question sit here about 5 seconds. You'll read it, and then I'll just circle the answer and begin my explanation. You can obviously fast forward to any question you like. This was the most missed question this year. It's about energy levels and the hydrogen atom. You may recall from page 3 of the reference table, if you have an electron with an energy that's the difference between this number and this number, but it doesn't have to do that. It could also go to the second energy level, and from there it can go to the third. So in total, there are 3 photons we're going to see from various electrons as it comes down in one of those 2 sequences. Not that the question asks, but these 3 energy levels, or the 3 energies the photons would have, would be these 3, corresponding to the step sizes, the differences between the energy levels. Fun fact, if you need to calculate the frequency of these photons, you could use E equals HF. Another fun fact, you can only use that equation if you're using joules, so you'll have to convert electron volts to joules when that time comes. But not this question. Question 2. Now the biggest mistake people make is that they think of this as a light wave. When light goes into a vacuum or air, it speeds up compared to water. But this is about a sound wave. A sound wave is a mechanical wave. There's something physically vibrating, and that vibration is going to travel fastest in solids where the atoms are very close together. A little slower in water, or liquid rather, because the molecules are a little further apart, and slowest in gas because the molecules are further apart. But there is an even better way to know the answer to this question. They gave you the speed in water. And they give you the speed of sound in air. If you convert this to regular number, that's 1,490 meters per second versus 331 meters per second. So it's clearly faster in water than air. By the way, pretty much any wave does not change its frequency. This stays the same. It's what I like to call the social security number of the wave. So it always stays the same when you have a wave interacting with 2 materials. Question 3, 33%. This question is evil. So it's not really evil. You just have to keep in mind that the diagram and what you think of as incidence is not the same. The angle of incidence is always relative to this line called the normal. The angle in this picture is not the angle of incidence, but this and this are 90 degrees, so this is 25 degrees. So the angle of incidence is 25 degrees, and for regular reflection, the reflected angle is always the same as the incident angle. So the reflected angle is 25 degrees. Have not seen a question about this word since pre-2002, but if you have a bumpy surface, that means the rays are going to reflect at different directions. That's called diffuse reflection versus regular reflection over here. Question 4. One, let's make some sense of this, of what's important and what's not. My ability to draw a truck, not important. My students will understand the flag. Drawing some sort of picture to help you see the big picture, however, is important. Also identifying what numbers in this problem are important. This is the height that the truck goes up. That matters a lot. Versus this, the length of the hill actually doesn't matter at all in this scenario. This, the weight of the truck, is going to be important. The Regents, for whatever reason, does love them some scientific notation. Sometimes I find it easier to think about it if you make it a regular size number. Which is the same thing as a watt, which gives us our answer. Question 5. Answer is 3. I do apologize for the one that keeps coming up on the screen. That's my hotkey, and it's easy to push other keys. All the other good hotkeys were taken. Here we have the equation for work, but what most people don't always consider is that this is really the force parallel to the displacement. It's technically a dot product, but for Regents physics, it's the part of this force that is sideways. It's not all of this 20, it's just the projection of this 20 onto here. In other words, the x component of this force in this case. So that is going to be the force times the cosine of theta times d. So 20 times the cosine of 25 times 4 meters, which gives us 73 joules. Or while we're at it, you could have left that as Newton meter for the unit. That would be perfectly acceptable. Behold question 6. Choice 4. Impulse, J just cuz, is simultaneously change momentum, which is m delta v, and it's also force times time. So that's 3 kilogram meters per second times 6 newtons times time. That time is going to be equal 1/2 of a second, which is our answer. So I can't resist this question. Imagine you have a car going 60 miles per hour, and it stops like a normal person applying the brake. And then you have an identical car, also traveling 60 miles per hour. But to stop, it decides it's going to drive into the world's most poorly drawn brick wall. Which car experiences the greater impulse? Trick question. Well, not really a trick question. You just need to know what you're doing. The answer is, it is exactly the same impulse. It's the same mass and the same change in velocity. The difference is that the car on the left here has a little force times a big time, the preferred way of stopping, whereas this car has a big force and a little time, a little rougher. Question 7. The answer is 1. We have electromagnetic waves, which require no medium, and we have sound waves, which are mechanical waves that do require a medium. As for longitudinal versus transverse, I'm going to show you a gratuitous Desmo simulation I made. And you can go here if you ever want to try it. Shows a number of things. This is transverse wave. This is longitudinal wave. So both of these, the wave is propagating, let's say, to the right. In the transverse, the molecules vibrate perpendicular to that, and in the longitudinal, they vibrate parallel to it. Now, these molecules won't actually travel from one end to the other, but their vibration shares the same direction, same axis as the propagation itself. Sound waves, by the way, are longitudinal. It's the air molecules vibrating back and forth. You can even envision those air molecules pushing your eardrum back and forth. Electromagnetic is like you might expect. It has an electric field and a magnetic field. Both sinusoidal waves, both perpendicular to each other. Prepare for a terrible diagram, but if this is the electric field, I apologize, I'm really bad at drawing this, but imagine this blue one was perpendicular to this red one. That's what an E&M wave would look like. It wouldn't require a medium, it would travel at the speed of light in a vacuum, but it would carry energy. So that leaves us with choice 1. Another tidbit to keep in mind, the way you generate an electromagnetic wave is by having a charged particle accelerate. For example, electrons in the antenna of a radio station accelerate back and forth very quickly, creating electromagnetic waves that then carry the information that we'll hear on the radio. But radio waves don't actually carry sound. They travel at the speed of light, and they just carry the information. That's another big misconception, that radio waves travel at the speed of sound. They don't. They travel at the speed of light. That wasn't even in this question, but hopefully it's useful. Wave-particle duality. Check out this question. So physics is weird, and one of the weird things is that particles, if they're very small, can do wave things. And waves, light waves for example, can behave like particles. That's the photoelectric effect. But in this question, it's saying, what's an example of matter acting like a wave? So it's not going to be choices 3 or 4 because those are photons. They don't have mass. And momentum, well, particles have momentum. That's not a big deal. But electrons can diffract, meaning if you have a bunch of electrons and you fire them through very small slits, they'll make a pattern here with high intensity, low intensity, very similar to what waves would do. Or not even getting that fancy, just electrons going through a slit will spread out. They won't all land straight in front of you. It's weird, but cool. So that would be an example of matter acting like a wave. An example, not that it was in this question, of light acting like a particle would be a photon coming in and then striking a piece of metal, for example, and causing an electron to leave, getting it to be ejected. That would be the photoelectric effect. But wave is duality. It acts both like a particle and like a wave. And matter, when it's small enough, does the same. Cool but weird. Question 9. 1. Decreases. Classic vector question. You have to know this. The largest sum of two vectors will be just adding the numbers. So in this case, 6 and 8 being 14. But that's only true when they face the same direction, 0 degrees. If they face the opposite direction, the resultant, the name for two vectors being added together, would be 2. But it'd be to the left because vectors have direction. The bigger one's to the left, 8, 6. The difference between them is 2. So the biggest magnitude you get is when the angle between them is 0 degrees. That's just adding them. The smallest is when they're in the opposite direction, 180 degrees. Then you just subtract them. Everywhere else is somewhere in between. So what do you think it would be for 6 plus 8? It's going to be smaller than 14, bigger than 2. How would you get the answer? Well, 90 degrees is nice because that's a right triangle. So you can just use the Pythagorean theorem. You may recognize the 3, 4, 5 triangle. That's going to make this 10. And obviously 10 is smaller than 14, so that's why our answer is number 1, decreases. But you may be wondering, what if it's at some weird angle? Like, what if we wanted to add 6 to 8? Well, one way is to do what's known as the parallelogram method. I find this is most useful for multiple choice questions. And what you do is you draw the rest of the parallelogram. So like this side is parallel to this and the same size, and this is the same size as this, and the resultant there would be like this. So you might have to, on a part 2, draw that to scale, for example. And some bonus knowledge, sometimes you'll be given 2 vectors, and instead of being asked to find the resultant, you're asked to find something called the equilibrant. That's the vector that would bring the others into equilibrium. It's also the same thing as the resultants, just 180 degrees the other way. So this orange one is what's known as the equilibrant, whereas this is the resultant. 10. 2 kilograms. You really don't have to think that hard. They're kind of setting you up like this is a weight question. Weight equals mg, but that doesn't help you here. The difference between mass and weight is that mass is the same everywhere you go. It's just the amount of stuff that's in you. So if you go to another location, whether it be Mars or somewhere else, your mass isn't changing. Weight is how hard gravity pulls on you, and that matters where you are. On the surface of Mars, you're being pulled down a little less hard than you're being pulled down on the Earth's surface. So weight does scale to mass, it's proportional. So the mass matters, but it's not the same thing as weight. So I have an expression. If you want to lose weight, go to the moon. If you want to lose mass, go to the gym. Question 11. 4. Weight. Here's the deal. Centripetal is not actually a force, despite that word force being there. Centripetal is direction. It's like downward force isn't a thing. Gravity is what's actually pulling you down. It just happens to be going down. Now I can't resist showing you another Desmos I made at this link. So I don't know if you heard that, but I was saying the Earth is pulling on the satellite, satellite's pulling on the Earth, it's causing the satellite to go in orbit. The direction is towards the center of the Earth, but the actual force is gravity. Interestingly, the acceleration of the satellite is not 0. You think of it as being weightless, but really it's just that you're going very, very fast, and you keep continuously falling around the Earth. Fun fact, the further away you get from the Earth, the more time it takes to go around. So a near-Earth satellite, like most of them are, take about 90 minutes. Whereas if you go about 6.5 radiuses away from the Earth, a satellite takes 1 day to go around. That's a geosynchronous satellite. And if you go about 60 times the radius of the Earth away, it takes 1 month to go around once. You know, like the moon. 12. The answer is 1. Like before, we talked about sound is a longitudinal wave. Again, a gratuitous Desmos. So the wave propagates this way, the energy is traveling this way, but the individual molecule doesn't move very far. It just oscillates back and forth with the same orientation, east to west. It's just not actually going to the end, not traveling. So vibration is not the same thing as traveling. Again, versus transverse waves, which vibrate perpendicular to the direction of propagation. 13. And man, do words matter. This is asking for the net force. If we draw the forces acting on this, there's a weight force pointing down, but there's an equal normal force pushing up from the index card. Those forces are balanced, net force is 0, otherwise the coin would accelerate. 14. The answer is 4. This is all about conservation of momentum. This is about the momentum before being equal to the momentum after of the system, not the individual pieces. The momentum changes between the pieces, but the momentum of the system combined is unchanged. The momentum before of the system equals the momentum afterwards. Now we just have to account for the momentum of all the pieces. So that's mv plus 0, because the big block's not moving, is going to equal afterwards you have little m plus big M when the bullet embeds, times the mystery the prime velocity afterwards. So the velocity of the system afterwards is going to be little m over little m plus big M times the initial velocity. That's choice 4. So when you have these kinds of problems with these collisions, you have a couple scenarios. One is what you have here, which is what's known as a completely inelastic collision. Sometimes you have what's known as an elastic collision, which for our purposes means there'll be two objects afterwards moving. And the third kind you sometimes have is the opposite of an inelastic collision, where you have something and then it explodes. And you have two pieces going in opposite directions with equal but opposite momentum. In that case, what you'd say is the momentum of the system before was 0, and it has to stay 0 afterwards. But in this problem, this is the answer. 15. 2. This problem is about one word: superposition. So when you have two or more waves, they add together. So you've got, I'm going to call this the red pulse plus, let's call this the blue pulse. So the blue pulse is kind of like -2, and the red pulse is kind of like +1. So this is what we're going to get when you add those two together. This is going to be kind of like -1. Also worth noting that these two pulses are going to pass through one another. They don't bounce or stop or anything like that. But the answer to this question, choice 2. Question 16. 1. Let's think about what equation we would use. Well, work is force times distance, and force is kind of like m times a. So work is like m a d. That's going to be kilograms meters per second squared times meters, which is going to be kilograms meters squared per second squared. Question 17. The thing is that ammeters measure the current through them and voltmeters measure the voltage across them. That means that ammeters are always going to be connected in series with what they're measuring, and voltmeters are always going to be connected in parallel. So this is measuring the current I1 going through here, and this is measuring the voltage across R2. Voltmeters don't go in series, ammeters don't go in parallel, and again, ammeters don't go in parallel. Question 18. $49 watts. Remarkably similar to an earlier question. So if power is work divided by time, that's also going to be the change in the total energy divided by time, which is going to be the change in potential energy over time, which is going to be mgh divided by time, or 2 kilograms times 9.8 meters per second squared times 15 meters divided by 6 seconds, which is going to give us our answer. 49 joules per second. By the way, a joule per second is the same thing as a watt. So power is the rate that work is done, and the unit for power is a joule per second or a watt. You could also have done force times distance over time, where the force is the weight, which is mg. 19. The answer is electric field strength. And at this time of year, you may be a little woozy going, what's electric field again? Electric field is a force per charge. It's a way of talking about how strong the electrostatic force is without having to know how much charge you're putting there ahead of time. Another way to think about it, it's in units of newtons per coulomb. It's the number of newtons a 1 coulomb charge would feel in terms of force and direction. This is in ohms, this is in volts, and this is obviously in coulombs. That's not a coulomb, that's charge. Coulombs. Question 20. The answer is 1. So first thing you have to recognize is that light slows down when it goes through lucite, or really almost any material compared to a vacuum. There's a formula here for that speed, and we just need to know what this thing called index of refraction is for lucite. So for lucite, it's 1.5. So 1.5 equals 3 times 10 to the 8th meters per second over V. V is 2 times 10 to the 8th meters per second lucite. Then you just take this and plug it in here, like this, and you get that, the answer. Question 21. The answer is 12. Let's talk about why. So modern physics, particle physics, for the purposes of the Regents, is basically a game. Everything that the universe is made of is either made of leptons, which is one of these 6 particles or their 6 antiparticles, or you're made of quarks. You're either made of 3 quarks, in which case you're a baryon, or 2 quarks, in which you're a meson. Part of the game is that if you know it's not leptons, always just assume that it's made of 3 quarks, because that will usually get you the right answer. Since we've got 2 protons and 2 neutrons, that's 4 things, each with, by default, 3 quarks. That gets you to 12. 22. Don't overthink it. The answer is 2. The reason is they gave it to you. Don't get distracted by all the pretty pictures and numbers. This is really a question about Newton's third law. B is pulling on A, and A is pulling on B in equal amount. This is very similar to the Earth pulls on the moon just as hard as the moon pulls on the Earth. So like the force of A on B equals, while the force of B on A equals, and like that's pretty much the same equation, because it is. Again, Newton's third law. When A pulls on B, B pulls on A. 23. The answer is 1. This is a straight up friction question. They tell you it's asphalt and it's dry and rubber. So rubber on dry asphalt, kinetics into the coefficient of friction. So you just plug in. F equals 0.67, which by the way has no units. The other thing in this course that has no units is the index of refraction. Times the normal force, which is 60 newtons, which is 40 newtons. Good job. 24. The answer is 1. I think 2 things. I think that it printed funny instead of the omega symbol, or the ohm symbol rather. And also because it's a variable resistor, which you don't see too often. It's still just Ohm's law. R equals V over I, or I equals V over R. When the resistance gets bigger, the current gets smaller. And the voltmeter stays the same because it's the same battery, the same potential source. 25. On the one hand, potential difference is in electron volts. It's volts. Current, Q over T, is coulombs per second. And choice 4, electric field, is force per charge. So that's newtons per coulomb. So that's actually going to be the answer. And as far as resistivity, ohms divided by meters, it's supposed to be ohms times meters, which you can either look at the resistivity table and see that that's the unit, or you can see R equals rho L over A equals RA over L, which is like ohms meters squared over meters, which equals ohm meter. In any case, the answer to this is 4. 26. The answer is 1, towards the center. When something is going in a circle at constant speed, the force is towards the center, the acceleration is towards the center, and the velocity is tangential. So C would be the direction of velocity, and A would be the direction of acceleration and net force. Again, the centripetal is merely a direction. Something has to provide that centripetal force, whether it's the gravity pulling the moon in a circle around the Earth, or the friction of the tires on a race car making it go in a circle. 27. The answer is 1. The easiest way to see this is to recognize this formula because it's newtons per kilogram. That's like force per mass. So this is going to have the same units as acceleration. By the way, as an aside, one type of acceleration, g, you think of as 9.8 meters per second squared. It is also 9.8 newtons per kilogram. Fun fact. 28. This one's a little annoying. It just revolves around this equation. One way to do it is to take values from this table and plug these in here and solve for the mass of the mystery thing. And then once you know that mass, to plug back into this formula and solve for the mystery distance here. But let me show you a little bit of a clever way to do this. Let's take the force at position A and divide that by the force at the mystery position, which we'll call just F. It's going to be G, mass of the Earth, which is not changing, mass of the thing, which is not changing, over the distance to A squared, and then G, mass of the thing, mass of the Earth, mass of the thing, over the mystery R. This stuff is all the same, so that cancels. I apologize, I'm not writing out the intermediate steps, but when you go from here and solve this for R, this is what you get, a fraction of RA, like this, which gives us the answer. If you can think of an easier way, let me know. It just feels a little lengthy for a Regents question. 29. 29 is 3. The biggest mistake people make is thinking that this is the amplitude. It's not. It's from the midpoint to here. But they didn't give D and A as a choice. A and E would also be the same size as the amplitude. So that's our answer. 30. The answer is 1. Don't overthink it. They gave us the frequency. We don't need the speed. So you just plug in 1/60 of a second. And that's it. 31. The answer is 3. Now let's back up for a second. What's going on? According to Einstein, the mass-energy equivalency, if you can make mass disappear, you'll get pure energy. So just as an aside, if you were to build an atom, I describe this as, imagine you went to the grocery store or the deli counter and said, I want to build, for example, a helium atom. You would need 2 protons, 2 neutrons, and 2 electrons. But if you had them put it on a balance and you get the mass of these, and let's go with atomic mass units, that's 1/12 the mass of a carbon-12 atom, you would find that you have more mass than if you assembled these together into a nice helium sandwich. So if you actually put the helium atom you assembled on there, it would have less mass. Where did the mass go? Well, to hold the nucleus together, those protons that don't want to be together, it takes a lot of energy to smush them together. That's called the binding energy. It comes from the missing mass. The name for that missing mass, by the way, not that you need it for this problem, is called the mass defect. So what they've done is they've given us the mass defect, but they gave it to us in something called universal mass units. Well, if you look on the reference table, it's 9.31 times 10 to the 2, the Regents and their scientific notation love, MeVs, or as I like to call that, 931 MeVs. That's per atomic mass unit. So you just multiply our 9.106 times 10 to the minus 3 atomic mass units, and that gives us our answer of 8.48 MeVs. So there's this much mass missing, corresponding to a binding energy of this, 32. 0 degrees. So superposition is the adding together of the waves. Constructive interference occurs when two waves line up pretty well. Now, as far as degrees, a whole wavelength out of phase would be 360 degrees, 90 degrees is a quarter, 180 is a half, etc. So let me bring up my simulation again. Now ignore the green one for a second. Imagine you've got that red pulse moving to the left. And at the same time, we're going to have another pulse moving to the right. Or the blue pulse moving to the right. And I'm going to pause this. So right now the red and blue are completely in phase, 0 degrees apart, 0 wavelengths different. Move it a little. And here they're getting less in phase. It's about 90 degrees apart. And they're going to keep going from in and out of phase. In any case, maximum constructive interference occurs at 0 degrees, maximum destructive occurs at 180. 33. 3. What we're going to do here is we're going to use both definitions, both change in momentum, m delta v, and force times time. We made the math easy with 1 kilogram. 1 kilogram times 3 gives us 3 kilogram meters per second here. And 2 to 4 is 2 meters per second times 1. That's 2 kilogram meters per second here. And then we're going to use force times time. 5 times 2 is 10 newton seconds here. And 10 times 0.5 is 5 newton seconds here. Newton second and kilogram meters per second, by the way, are the same. So the answer is 3. Question 4. I'm sorry. Question 34, the answer is 4. Resonance. If you time your feet swing so that it matches the swing of the pendulum, or as you call it, a swing, your amplitude can grow. If you were to try to swing where your legs were going in the opposite direction of the swing, you were trying to be 180 degrees out of phase, you would actually lose energy and start to slow down. But there are lots of examples of things resonating. It's not just a swing. The one people think about is trying to break a wine glass. If you sing at just the right frequency so that your sound waves are vibrating the air molecules at the same speed, the glass is naturally vibrating back and forth at low amplitude. It'll be like a dad pushing a daughter on a swing at just the right frequency, and the amplitude will grow and grow and grow. And in that case, you could actually break the glass. But there's lots of examples of things resonating. 35. Newton's third law alert. Newton's third law alert. This question is really about Newton's third law. It's not actually about gravity. The Earth pulls on the moon, but the moon pulls on the Earth just as hard as the other way around. So if this is the force of the Earth on the moon, this is the force of the moon on the Earth. They are the same magnitude. They're Newton's third law pair. 36. The answer is 1. This is a positively charged rod, so obviously, at least I hope obviously, a negative thing can be attracted because it's the opposite charge. What's less obvious to people is if I take something that's charged and I hold it near something that's neutral, if this is a conductor, what happens is it repels positive charges, or more accurately, attracts negative charges to the same side, leaving a positive on the other side. You have this physical charge separation. This is called induction, and you're going to have an attraction because these positives are closer to these negatives than they are to these positives on the other side. I sometimes liken this to seduction. It's like the electrons are being seduced to the same side. But there's a physical charge separation that only happens in conductors. By the way, you can also get an attraction to something neutral, like paper. If you've ever brushed your hair and had hair stick to it or pick up paper or something like that, the paper is not a conductor. What's going on? In that case, you have something called polarization. where the electrons can't move to the other side, but the molecules can sort of rotate in place because the molecule has a more positive end and a more negative end. It's kind of like a weather vane in the wind. This, interestingly enough, is exactly how the microwave oven heats up your food, because your food has lots of water molecules, and water molecules are polar, and in the electric field of the microwave, they kind of go back and forth. It's almost like you had a weather vane and you kept changing the direction of the wind. Cool stuff. 37. The answer is 3. So I'm going to show you yet another simulation. So we're comparing 45 to 60. And I actually have 2 simulations I'd like to show you. Here's the first one. So the red is fired at 45 degrees. Okay, now the red is fired at 45 degrees and the blue is fired at 60. And you can see the red one goes farther, but the blue one takes more time. The reason is the greater the angle, the greater the y component at launch of velocity, which means it's going to take more time to go up, slow down, and come back down. The time is dictated purely by the y component. The x component has no influence on the time of flight. The range, however, depends on a combination of how fast are you going sideways and how much time are you in the air. So it's like this trade-off. So if I was to change the angles like I was doing before, you'll see that. So if I change this, I'll change this one. Now the red one takes more time, it doesn't go as far. Now it's a trade-off. The optimal angle, at least for a ground launch, is 45 degrees. 45 degrees from the same height will cause it to go the farthest. Okay, and let me show you the second one I made so you can see a bunch of launches simultaneously. It's very pretty. So here's what it would look like if you launched at 0, 5, 10, 15, 20, all the way to 90 degrees simultaneously. 45 degrees still gives you the farthest range. 90 degrees still gives you the most time. Also worth noting is complementary angles give you the same range. So like 30 and 60, 20 and 70, etc. Plus, it's just really pretty. 38. The answer is 4. All angles of incidence. Because this is reflection. They're not asking about refraction. This isn't total internal reflection. This is, if you have a light ray come in, it's going to leave at the same angle. So if this is 20 degrees, this is going to be 20 degrees, always. And it doesn't matter what the incoming angle is, the outgoing angle will be the same, at least for a plane mirror. Or in this case, sound waves instead of light rays. So these are sound waves bouncing off of the ocean floor, but it works the same way. And I think it's pretty cool. 39. 4. P is V squared over R. All of these see the same voltage, 12 volts. Power dissipated in the 36 ohm resistor is just going to be 12 volts squared divided by 36 ohms, which is going to give us 4 watts, which is our answer. Finally, question 40. Woohoo! And for the like 12 people who get to the end of this video, the answer to this is 3. Although it's not just that it's too small, it has to exactly match a transition between energy levels. And if you're in the ground state, the smallest number of electron volts, at least for hydrogen, to go from here to here is 13.6 minus 3.4, which is 10.2 eV. And you don't even have that. By the way, if you gave it 10.3 EVs, that wouldn't be absorbed either. But at less than 10.2, you have no chance. So if you've stuck around this long and you actually kind of like this, if you go to mrhosey.com/review, you can find, I did this in years 2014, 15, and 16. A lot of the questions overlap, but not all of them, where I went through explaining these and other concepts. And if you're really, really wild, and this isn't actually the day of the exam, you can download my Excel-based program, which you can also find here. or directly at mrhosey.com/program. And I'll link to some of those other ones, 16, 15, 14. So good luck on the exam. A lot of it really just comes down to make sure you read carefully and you answer the question that is actually being asked. The most dangerous thing about physics is that you can understand the physics well. It'll feel so good. But if you're answering the wrong question, it won't matter. But otherwise, good luck. And as far as seniors taking the exam late this year, sorry. But if you're a senior watching this, good for you. So good luck.